So I am standing in for Paul McKenzie, the PI of this PRAC. Here's a list of several of the collaborators on the grant. I'd like to particularly mention that we have on the GPU side some help from Kate Clark and Matthias Wagner at NVIDIA. The rest of us are physicists. Okay, so we have several key challenges. The lattice QCD calculations that we do must support large experimental programs. If we can't do that, they can't get the information they need out of these expensive experiments. And one of the challenges is that QCD is a strongly coupled nonlinear quantum field theory. Because it's strongly coupled, we can't use typical Feynman diagram techniques that other people use in weakly coupled quantum field theories. And lattice QCD is a first principles calculational tool, but it requires large-scale computer power. It's not just a model, it really is the quantum field theory, and we regulate it by putting it on a grid of space-time points rather than treating it as the continuum. For this PRAC, we use two different actions, and there's actually two different groups involved in the calculations. One is called the Highly Improved Staggered Quark action. It replaces a less improved action. And we use that to study some fundamental parameters of the standard model that I'll describe in some detail later. These include quark masses and something called the CKM or Kobayashi and Muskawa mixing matrix. So we'll have more about that later. And we also use the domain wall action, which has very good chiral properties or very good properties for light quarks. And that's used to study direct CP violation in kaon decays into pi plus pi minus, for instance, and also the k long k short mass difference, which is known to very high accuracy, but we can not up till now predict it. Why blue waters? Well, first let me mention that the types of calculations we do, which have been going on, for many years on smaller computers, proceed in two stages. One is we generate gauge configurations, as we call them. These are snapshots of the quantum fields. And once we have those snapshots of the quantum field, which essentially are the Feynman path integral for the system, or elements in the Feynman path integral, we can store those configurations and calculate a bunch of different quantities from different physics studies. So the first stage is a stochastic evolution, and you want to do that in just a few streams. So you need a fast computer, or else you're waiting years and years and years. Okay, but the next part, once you have those jobs run, those can be done in parallel because each snapshot is analyzed independently. And on blue waters, we have used the GPUs. We need these large partitions to generate the configuration, so we need a big computer. And the second stage can be run in parallel if there's a lot of capacity, and we do that too. One important thing about blue waters is it was really one of the first computers that enabled us to calculate at very light up and down quark masses. In previous years, before blue waters, we would always make the up and down quarks heavier than in nature and have to do an extrapolation. That's generally called the chiral extrapolation. Well, we still do some of that, but now we have a really good handle because we don't have to really extrapolate. We have results at the physical light quark masses. Okay. All right. And basically, blue waters has allowed us to produce a number of results with unprecedented precision, and we'll see that later. And then the configurations that we create on blue waters are used by other groups, and the physics analyses actually often continue for years after the configurations are generated. And we do share our data. So we make these configurations available through HISQ. Unfortunately, there's no long-term storage on blue waters, so we can't serve them from there, but we have Ranch and HISQ resources. So the two, one of the two actions we used, approximately 60 new archived configurations with physical quark masses for up, down, strange, and charm quarks, and a lattice spacing of 0.04 4-2 Fermis were created on blue waters this year. Of course, there are many other configurations from earlier years. And the Fermilab lattice and Milk collaborations use these and will be using these for a number of years to study weak decays of heavy light mesons. And I'll talk a little bit about that later. Other groups also use the Milk configurations for a variety of projects that I have no time to go into. And occasionally we save the quark propagators themselves, but I won't focus on that. We don't tend to share that as much. With the chiral action that we use, those quarks, again, are called domain wall fermions. And they're a little bit even more interesting because they're on a 5-dimensional grid. There's an extra fake dimension that's the distance between the domain walls. And those are 64 cubed by 128 by 12. The lattice spacing is not as fine as the other calculation. It's 8/100th of a Fermi, and 150 molecular dynamics time evolutions were run on blue waters. And the physics projects include the anomalous magnetic moment of the muon. I'll talk a little bit about that later. The K long, K short mass difference that I mentioned before. And again, decays of heavy light mesons within domain wall formalism. Okay, here's a bit of machine information. So one of the things that was done with the domain wall calculation and explored this year was using the M-pitch rank reorder method. And so this is a command for reordering the tasks on blue waters. And this is a bunch of different runs on what the particular size I mentioned before. The green points are without the rank reordering. There would be a point up here if it hadn't timed out in 48 hours. And so I guess that was never done on 1,000 nodes. But the red points are with the rank reordering, and you can see they're well below the green points. So that was a win for that calculation. And if you are running big jobs, we suggest you try it. Okay, why it matters. Well, the standard model of elementary particle physics, it consists of 3 of the nature's 4 known forces. The strong, weak, electromagnetic are in the standard model. The 4th force, gravity, is not included in the standard model. There's a whole bunch of experimental method data going back about 30 years that support the standard model. But it turns out that there are a number of parameters that can only be determined from experimental input and actually need information from quantum chromodynamics, the strong force. And these include the quark masses, the strong coupling constant, which is usually denoted alpha S or alpha strong, and the CKM matrix elements that I mentioned before. However, there are also theoretical reasons why we think that the standard model is incomplete. And I don't really have time to go into that, but the holy grail in elementary particle physics is to find, not just verify that the standard model is correct, but find problems. And there are a number of measurements now where there are like 2 standard deviation differences between the standard model theory and the experiment. And so it turns out a number of these quantities or confrontations between theory and experiment really need input from the strong interaction. And that's what we specialize in. So one interesting example of that is the anomalous magnetic moment of the muon. It's often just called G-2. You might have seen that if you've been looking in physics journals. It could be a very interesting place to discover new physics. So it's one of the most precisely measured quantities in physics, and I have on the first line the experimental value, and in parentheses is the experimental error, and then the theoretical value and its error. They're comparable right now. But there's more than a 3 standard deviation difference between theory and experiment. And the issue has been for a number of years whether that really represents new physics or whether we don't understand the theory as well as we should. And to have more, you wouldn't claim a discovery on 3 standard deviations. So the experiment was initially done at Brookhaven National Lab, a huge magnet which was shipped up the Mississippi River and then trucked where you have to close the highway to move this big magnet. It was shipped to Fermilab, and the current experiment was reset up there. It takes quite a while to get everything all aligned. and it's now running, and the goal is to reduce the experimental error by a factor of 4. But if the theory error doesn't come down, well, you're still not going to be able to have the confrontation that you need between the two. So it's very important to work on that, and you'll see something about our progress in the next few slides. So the theory comes from a number of contributions. One is quantum electrodynamics, and that's been done with perturbative techniques up to 5-loop order. Then the weak interaction has been done up to 2-loop order. Then there are diagrams that contribute that depend on quantum chromodynamics or strongly interacting particles. This is what's called hadronic vacuum polarization, something that we're calculating and using blue waters for. And there's another process called light-by-light scattering that I'm not going to talk about. These two lines dominate the theoretical error, and we're going to show the status of the hadronic vacuum polarization. So what we have here is the value of the hadronic vacuum polarization. Again, this is one part. It's the part with the biggest error in the calculation. This point is what the value would have to be based on the experimental value if there's no new physics. So the hadronic vacuum polarization would have to be this. Okay, and the real question is there new physics? Well, these calculations are based not on pure theory, but based on looking at experimental data for E plus E minus annihilating into strongly interacting particles, and then using that to calculate hadronic vacuum polarization. And you see there's a bit of a spread that might give you pause as to whether they really understand their errors as well as they do. And then, and this has been going on, you can see the earliest reference is 2011. And then theorists realized, who were doing lattice QCD, that we could get into this game. You can see our errors are currently much bigger. And this is the calculation that the Fermilab, Lattice, HPQCD, and MILC have been doing, partially using blue waters. This, at the moment, well, it's preliminary for one thing, and it's kind of in line with some new physics. Here are some other recent calculations last November and this January from 2 competing groups. And there's a meeting in about 2 weeks to try and go over everyone's results and see where we are. Okay, how am I doing on time, by the way?
6 minutes.
Great. All right, so I'm going to skip over a little of this text. I mentioned the CKM Matrix. This is Kobayashi and Masukawa after they won the Nobel Prize. Look at how happy they are. All right. Here's their matrix. They got the Nobel Prize for realizing the significance of this 3x3 matrix. But then it's people like me and the experimentalists who try to figure out what the values are in the matrix. Okay, so what I've done is the matrix is these bold points, or bold values, and then below each matrix element I have some physical quantity, physical decays on which you could measure these CKM or determine these CKM matrix elements if you can understand the strong interaction contribution. So these are called leptonic decays, where we have a charged lepton and a neutrino in the final state. And then this is an example of a semi-leptonic decay where there's a strongly interacting particle, a pion, in the final state. And so we use blue waters to study these processes, the theory of these processes. And I'm going to concentrate on the leptonic decays in this talk, simply because there's not much time. So this is how a charm meson called a D decays leptonically. This is the theoretical formula. Most of this stuff is well known except for this, which is the CKM matrix element, which gets squared, and this, which is called a decay constant. So the decay constant is what we calculate on the lattice, on blue waters and elsewhere. And that was for a D. There's a decay constant for the pi meson. There's a decay constant for the K meson as well. And one of the things we do is measure the ratio. And so this is a very recent result from a December paper that's been submitted to physical review, D, and is on the archive now. And it's a comparison of this ratio, Fk over F pi. This is our new result. This is a previous result where we didn't have as much statistics and as many ensembles as we created. This is a competing group. This is HPQCD, which we sometimes cooperate with and often compete with. And these all have up, down, strange, and charm in the C. These are older calculations, some of which were, well, which have up, down, and strange quarks in the C, and the errors are all bigger. So before this calculation, the error was 0.23% in this ratio, and that was bigger than the experimental error that is what's measured. So the ratio of two experiments can be interpreted as the ratio of the CKM matrix elements to this ratio that we've determined on blue waters and elsewhere. And so by getting this value accurately, we can infer this ratio of CKM matrix elements, which is fun. And I don't know what exactly happened there. Oh, there we go. Okay, so that was light quarks, and now I'm talking about things with charm quarks. And so again, we measure some decay constants, and these are quite improved compared to our previous results. In fact, this is Fermilab lattice milk that I'm that's the group that's doing these calculations on blue waters with HISQ action. This used a different approach. The errors were quite a bit bigger, and this is before we were able to do our latest running on blue waters, and this is the current result. And this error is now at about 0.25%, and you could see 6-7 years ago how much bigger the errors were. Okay. Now, bottom quark, which is even heavier, presents interesting challenges, which blue waters is very important for overcoming. And there's, some details here, the calculations. So when A stands for the lattice spacing and MQ stands for the mass of the quark, and you get good results when AMQ is small. And it turns out if the quark is very heavy, as the B quark is, it's hard to maintain the product of AMQ being small. So empirically, we know that if on any given lattice spacing, if MQ is small enough that this is obeyed, you should get pretty accurate results. And it's easy to do for the charm quark, which is almost 5 times lighter than the B quark. So for the B meson, AMB is just below 0.9 for the lattice spacing I mentioned that we've been calculating on blue waters recently. We'd like to go beyond this, and in fact we do have one ensemble with a smaller lattice spacing that blue waters has contributed to. So blue waters has been very important for making the lattice spacing small enough. And here's a similar graph to what you've seen before for the decay constants from the same paper. And you can see the errors have been reduced by to 1.2 to 1.4 MeV. It's about a factor of 3 reduction. Okay, let me skip this slide. This mentions something about the ensembles that we have created on blue waters, not all this year. This is the ensemble that we've been working on this year. The others came earlier, and a little bit about some of the papers we've produced. And now I will just let my conclusions stand so you can read.